Welcome to this example of multi-domain code simulation using APIs. In this video, we're going to illustrate how AutomationStudio can use APIs to communicate or to co-simulate in real time with third-party simulation software. We will showcase how AutomationStudio can be used to model complex simulation environments and exchange data in real time with third-party simulation software. In this demonstration, we're going to apply this concept using AutomationStudio and MATLAB. On the AutomationStudio side, we have created a model of a front-loader mechanism, which is a typical accessory in construction and agricultural equipment, which contains a hydraulic design using components from catalogs with mapped expected performance based on manufacturer specifications, and its mechanical environment represented by a mechanism with component masses, inertias, and external loads, which will transfer the mechanical loads to the hydraulic model, creating a complete virtual representation of the design. This project also features emulation of set-point devices such as a joystick to control the motion of the machine and loads on the mechanism that can be modified by the user. MATLAB will be used on this demo to create the control algorithm using Simulink for the electronic valves, which can be modified, validated, and optimized at any point during the design stage of the machine. The communication between the two software is achieved through the use of APIs to create a data bridge. This bridge consists of Windows APIs coded by Famic to enable the communication, but custom solutions can be created by users experienced on programming languages. The architecture of this communication is presented now. Since data is evaluated differently by both AutomationStudio and MATLAB, a third element is necessary in order to achieve co-simulation. This is done by the bridge, which enables the two software to work on a server-client configuration. On the AutomationStudio side, data is evaluated by the simulation engine at each simulation cycle, which can be modified by the user, allowing for real-time data trending and analysis. On the MATLAB side, typically a given data set is fed to a model to produce an output, which is then analyzed without a fixed simulation time. The Bridge API allows the assignment of active and passive roles to both software to achieve the synchronization of the data by allowing AutomationStudio to perform one simulation cycle, collecting the data and set the simulation in listening mode or waiting for a reply. The API then sends the data to MATLAB, which is fed to the Simulink model. Then an output is produced, it is collected, and sent back to AutomationStudio to perform another simulation cycle. This is repeated again and again so that co-simulation is achieved. The key parameter to this co-simulation is computer performance. This can be impacted by the complexity of the model on both sides and the amount of data transferred. Going back to our system, the hydraulic model on AutomationStudio contains electrical valves that control the motion of the front loader, and emulated set-point devices for manual or automatic actuation. In this demo, we will showcase an automatic sequence for the command signals so that tests can be carried out repeatedly with the same input conditions so that different control algorithms can be tried out. The first thing needed is the identification of the signals that will be needed to be exchanged between the two models. That is, the command signals for the boom and the bucket, the mechanical feedback provided by the position of the actuators, and the boom and bucket positions. The expected data to be returned will correspond to the electrical signals needed to control the valves for both the boom and the bucket. On the MATLAB side, it is needed a control algorithm that would take the input signal from the hydraulic model and produce an output for the electrical valves. This is achieved by implementing a Simulink model. On this model, you can observe the blocks that are used to collect the input data, the PID blocks that will compute the actual control, and then the output blocks that will send the output back. The Simulink model needs to be compiled and analyzed to make sure that there are no runtime errors. Another aspect to consider during the co-simulation is that it is not possible to communicate data directly to a Simulink model. This has to be parsed through the workspace environment on MATLAB, which is the final link on the communication chain. The data server has to cope with all this data handling, which is done by using simple scripts on the MATLAB side. First, the communication initialization script, which is used to define the variables on the server that will be used to exchange data, which contains the variable corresponding to the command signals, the feedback from the mechanical model, and of course the output produced by the Simulink model to control the electrohydraulic valves. Second is the script that transfers the variables from the data server to the workspace environment on MATLAB, launches the Simulink model, collects the results, and sends the data back to AutomationStudio. There's another script that can be used to test the Simulink model before attempting the code simulation. This is meant to feed the model with test data just to verify the communication between the Simulink model and the workspace environment. Once the communication has been established from the MATLAB side, the variables for the communication are created on the server. The message is displayed to the user, and MATLAB is set to listening mode, waiting for AutomationStudio to send data. On the AutomationStudio side, once code simulation is established by launching an API, a message is displayed and all the variables defined on the server are mirrored on the AutomationStudio project. Of course, for this variable to have an effect, there is a variable assignment that is needed so the user can match the variables coming from the server to the corresponding components on the AutomationStudio simulation. Once the simulation starts on the AutomationStudio side, the event is detected by MATLAB and the data exchange commences, as you can see now. Observe that the code simulation is being successfully done in real time, as is clearly shown on the AutomationStudio time graph and the MATLAB interface, on which we can see the control signals coming from the Simulink model reacting to the command signals provided by the automated sequence on the AutomationStudio side. This code simulation enables a multi-domain analysis using different tools that can greatly speed up the design process, with different disciplines involved early on in the design stages of the machine, which can boost efficiency by reducing the design times and fast prototyping. Thank you for your attention to this demonstration. If you need more details, please contact a representative of AutomationStudio.